So our next speaker is Clecio Bom with the Standard Siren measurement of the Hubble constant following LIGO, Virgo and KAGRA. So whenever you're ready.
Thank you for the opportunity to speak here. Thank you for the organizers. It's an honor to be here in front of Copernicus, you know, and to be a representative of South America here. I don't see many people from South America here. So today I'm going to speak to you about gravitational waves, dark standard siren. So we are switching gears to gravitational wave again. And I'm talking about the last results I have in collaboration with many collaborations, mostly with Antonella Palmesi and Viviane, a postdoc working under my supervision. So as many of us are here, we all know there's a huge tension in the Hubble constant. It might be between direct or indirect measurements, if you prefer late and early measurements. So today I'm going to talk about these large constraints here over gravitational waves and how they got improved since the last LIGO run. Just a recap of how gravitational waves work. Well, there's LIGO, Virgo, and KAGRA. They work together. They can detect binary neutron star, black hole mergers, and neutron star black hole mergers, mostly, okay? So we expect from the neutron star merger electromagnetic counterparts. There's been some discussion early this morning about this. In terms of neutron star black hole, we also expect an afterglow, but nobody has ever seen a counterpart yet. And for binary black holes, there might be some models can point it out that it might be some flare, but it's very hard to detect. However, well, gravitational waves are, the detectors are not good to localize the event. So we don't actually find the counterparts because the areas are huge. So 10, 100, and sometimes 1,000 square degrees for search. I'm working in some collaborations trying to find these counterparts. And it's a very huge area and it's a very fast transient, so it's really hard to spot. You have a couple of days to find it, so it's not an easy task. So, but they are also very good to get the luminosity distance. Okay, so they give you the luminosity distance, and if you have the redshift, you can actually use them as a standard siren and obtain H0. Okay, so that's the deal. You get the luminosity distance from gravitational wave detectors, and with the Z, you can obtain H0. So there has been a lot of promise on this field. This is the first constraint for a bright siren, as we say, the binary neutron star. There was this famous forecast that says that in a couple of years, we are almost there. We would reach something like the 2% level necessary to arbitrate between CMB and supernova 1A kind of measurements. However, this actually didn't happen yet because we only found one bright siren, which is the W170817. There was a couple of kilonovas, which is neutron star mergers or neutron star black hole mergers, and possibly white dwarf neutron star merger that happened since then, in these last 7 years. However, they were not detected as gravitational wave counterparts. Okay, they're only detected in the optical. Okay, mostly with short GRBs or extended emission GRBs. So the forecasts for detectable BNS are not that good for this current season of LIGO observations. So we have up to 0 neutron star mergers to be detected. That's the current constraint. So not so great. Man, but life is what it is. So what can we do? Even if the LIGO detects the binary neutron star, this is a strategy paper I did for DCAM follow-ups. It's not always you see the afterglow. If it's as bright as GW17 or 817, this is the two different strategies for observing. It's likely that you find up to the limit of this current season of LIGO detections. However, if it's like reddish or more like what we would expect for a neutron star black hole merger, this is hard. At the end of the LIGO sensitivity, we would see something like 50% in an optimized strategy with a wide field camera with everything on your favor. Okay. So what can you do if you don't find it? Because simply LIGO doesn't detect it, because there might be not so many in the nature. You can use dark siren method. Okay. So dark siren method is a quite simple idea. Instead of relying on just a single source, you use all the galaxies over the big region and consider them as a possible host galaxy. Okay? So you sum up all the galaxies in your catalog. You consider the bias on your redshift if you are using photometric redshifts. So the likelihood is quite simple. It's a Gaussian here. The dependency is in the luminosity distance from LIGO and from each galaxy that you contain in your catalog. Okay, so summing up with marginalizing over the redshift errors and the bias, you can obtain a very nice, well, not so very nice, but a nice constraint over H0. Okay. So some highlights over this dark siren method I'm about to present. So we always do a blind analysis, so we don't actually see the constraints until the end. So we made a lot of photo-Z validations. We produce our own photo-Zs, and I'll tell you a little bit more about this. We use several cuts to remove very bad galaxies in our catalog, some sort of color cuts to remove stars and bad detections. So we also define a selection function from full bistar simulations, from gravitational wave simulations. And we don't use luminosity weights, okay? So, there are some people that use luminosity weights, so they put more weight over some sort of galaxies. Sometimes the stellar rate, stellar formation rate is one of the possibilities, but I'm being agnostic here, so no luminosity weights. So LIGO also give their own constraints. What are the main difference between LIGO work and the work I'm presenting to you right now? Well, they didn't have their O4 constraints yet, okay? So I'm talking about the last season. So what they did, so they usually assume a BBH population, and they fit over the BBH, the binary black hole population, okay? So they use, our photo-Z goes up to a higher magnitude because we're using all the DCAM footprint. We also considering a full probability density function for each of galaxies. So the photo-Z contains the full PDFs, not only the most likely photo-Z and the error bars. And at least in the last catalog, the last constraint they released, they use the GLAD catalog, which is whole sky catalog. However, it's a little bit incomplete, so it has and highly homogeneous. Okay. So what we do, I got all the DCAM public released area. Okay, so all the pointings of DCAM, all the images over DCAM that are public, and we select by the coverage. So over 70% of the probability of the LIGO constraints on where should be localized the merger. And we also keep in a low distance, so we don't have much dependency of omega matter. So we select those events. This is from the previous paper from myself and the collaborators. And these are the newest ones with the O4 data, the current run of LIGO data. Okay, so we also rerun the other 5 events because LIGO updated the sky map, so they reduce the area, which makes our constraint a little bit better. Okay, so we use our own photo-Zs. We produce by a deep learning algorithm. that is a mixture density neural network, so it can produce the full PDFs, not the point statistics. This is a nice thing. For instance, I'll point for 2 examples here. You can obtain some degeneracies, like the multiple peaks that we find in here, that happens in some of in our PDF. So this doesn't appear if you only use the pointing statistics and not the full PDF. And this is hard for me to read here, my own legend. Oh, I can't look here. Okay, so this greenish is the public legacy survey, PhotoZs. And the red one is spec Z. So we got interesting constraints over the PhotoZs, and we are using this. This is currently under the Delve internal review. Delve is a collaboration that covers 17,000 square degrees in DKN area. Okay, so these are our main line plot for the PhotoZ, so we have an idea how is it, and we can make validations over the PDF because we have the PDF. So this is the PIT test that show a little bit of overconfidence, a little bit of bias towards the small values of Z, but we correct for that. This is the odds, and this is the point statistics that we use. So we have less bias in higher redshift, in up to redshift 0.5 compared to the public legacy ones that are only point-like, so that we cannot compare the PDF statistics. We also have lower error bars over the points around the end of the PhotoZ range we are considering, and we are similar in terms of outliers here. Okay, so this is a plot that we use to guide ourselves to make it as a cross-check, and if everything goes, this is the overdensities over each of, in this case, I'm showing 6 gravitational wave events. So I'm pointing here the actual, the mean luminosity distance from LIGO, okay, and the error, okay? But I converted using H0 equal to 70 to Z, so I can see where are the overdensities on each event. Because we know that in the dark side business, we can actually see these peaks of overdensity over the posteriors. So this is another check. So we can see how we have overdensity of galaxies over the mostly likely value of luminosity distance. Okay. Okay. So this is a comparison between using the full PDFs, using a Gaussian approximation over the full PDF. So I'm only using the error bar. And the legacy public data. Okay, we see that this can make a huge difference in some cases, like this one, where the posterior for a single event is not very informative. If you're using the public version, for instance, and the Gaussian approximation are also a huge deal depending on the event. Some of them are in almost completely agreement, it doesn't make a lot of difference, and some of them we can see some difference over the posterior here. Okay, so these are our new events and the event that we run again, 8. These are posteriors, so we combine these posteriors and to obtain our final estimation. Okay, so as you can see, this is the dark siren constraint. It's still a little bit wide, and the combination with the single bright siren. Okay, and this is the Planck and the supernova constraints you can see here. Okay, thank you. So these are our main results. So using the 15 dark sirens that we have up to now, using the full coverage of DCAM data, public data, that we redo all the PhotoZs by ourselves, we can reach this number, 69, with the error about 12, so have 18% precision here. If you consider the single bright siren without viewing angle constraints, which are depending on astrophysics assumptions, you see around 20%, as you can see here. Okay, so the 15 dark sirens could get a better precision than the single bright siren without another astrophysical constraint. If we combine everything with the afterglow and the jet constraints, we could reach this one, 768 plus minus 4, precision of around 6%. So, and the dark siren in particular, they reduce around 10% the best constraint over the bright siren. So how do we quantify the tension? Where the constraints of gravitational waves are pointing to right now, right? So we are using a metric proposed by Finney et al., whereas we have the posterior predictive distribution when we evaluate whether the data we are using are coming from the same model, from the data of others. So we make this comparison between gravitational waves, Standard Sirens versus Planck, and gravitational waves, Standard Sirens versus supernova ONA. If you use only the 15 bright sirens, that's wide constraint, we don't see much. We use the PPD ratio as a quantifier for this tension. We see that there is no preference between Planck, 99.5 and 97.4, between Planck and Schulze and the dark siren constraint. As expected, there are very wide constraints. However, if we use the full combination, bright siren, afterglow, jet constraints, everything together, we are starting to see at least a pointing towards the Planck, the Planck H0. That's what we got. This is a very preliminary results. We know there's a lot of things to do. The jet constraints and afterglow depends upon astrophysical assumptions. There's also a huge deal in how to work with possible systematics over dark sirens, but this is just to give you a picture of what's going on. So the dark siren, my concluding remarks are dark sirens need high precision photosys and fairly completely cataloged. So legacy, rubbing, JPass are surveys that we are it would be very interesting to do this job. Up to now, we have 15 events, 12% precision from dark sirens only, using the first part of the O4, the first part of this season of LIGO. So they have more data to come. LIGO will run until next year, so we can potentially have many more dark sirens over it. And we got this 12% against the 18% of a single bright siren without afterglow and jet constraints. This is an interesting thing because electromagnetic counterparts outnumbering 2, at least. We have hundreds of gravitational waves from BBHs, from binary black hole mergers. Then we have from neutron star mergers that we actually don't have any other constraints since from the past 7 years. And well, systematics should be investigated, simulation of the catalog completeness, preferences of hosts, the different channels that can, where the BBHs can arise, for instance. So can we make a well-defined weights? You can think about of using in very well-localized ones only spectroscopy. This would reduce and help a lot the constraints, for instance, from DESI or from most. But we also should evaluate the impact of all possibles of systematics in photometric redshifts. Well, thank you very much for your attention.
Okay, questions?
Very nice work.
Thank you.
So your documentary survey, your limit is 22 magnitude, right? So, but then if you go to higher redshift, your galaxy catalog is sampling brighter and then more luminous populations only, right? So my question is, how much? Then you never know your gravitational wave is coming from the luminous galaxy that your documentary survey is covering. It might be coming from the dwarf galaxies that is, out of the sensitivity limit of dark energy survey. So my question is, how much of this result depends on the limiting magnitude of your catalog?
Not really. We are actually fitting the structure of the galaxies. So we don't really, it's not really necessary to the specific host to be in the sample. Is that what you ask?
Okay, you are sampling the galaxy over density.
Yes, sort of.
Taking a redshift, right? But there's no guarantee that
the host is there. No, there's no guarantee that the host is there. So that's why we have multiple peaks, because we see the structure of the large-scale structure. That's why you need many. Overall, there's a couple of papers showing that if you sum up many dark sirens, you finally get the right H0. So that's the deal. If you're using a single one, you find multiple peaks, you find a very uninformative constraint.
So you sample many dark sirens, then majority of them are coming from overdensity. That's
yes, in the regions of overdensity.
Thank you.
Thanks for the interesting talk. So, if I understood correctly, you said that you don't assume anything or something like that about the binary black hole population. Is that did I understand correctly?
Yes.
But in the LVK-O4a cosmology paper, it was shown that this is a very crucial thing, because actually you can get H0 constraints without any galaxy catalog whatsoever, just from the binary black hole population modeling. And in fact, this affects the dark siren methodology because it comes as a prior in your analysis. So can you say a bit more why you think it's not relevant, why it doesn't affect?
Yes, you're right. They use the BBH population assumption. So if you look through the LIGO paper, most of the constraint comes from the BBH assumption. Is that what you mean, right? The BBH population is a huge deal there. One likely reason to do that is because of their catalog are not very informative. So that's the difference.
Yes, that's true, but even if your catalog is somewhat informative, you have to use both, because you have to model the BBH population somehow. You cannot just say, not assuming anything, assume something, because it's your prior. In your equations, there is a prior on the detection rate of the BBH. This comes exactly from that, yeah?
The thing is, the reason I say we don't assume the population is the fact that we don't put all the galaxies are equal to us as a possible hosts at this point, right? So in this sense, we don't make any other assumptions, and we don't fit the matter the matter distribution of the BBH population as they did.
Okay, thanks.
Does it make sense?
Kind of following up with the first question, makes me a little bit nervous that you need a complete catalog to be able to get truly unbiased constraints on H0, because I have seen papers that were talking about how if you don't have a complete catalog, depending on how you are accounting for that, you can be biasing the H0 that you get. So I guess my question is, one way that I feel like is kind of straightforward would be to cross-correlate binary black hole merger locations with a galaxy catalog and see whether you're following the same trends and whether you have the same 3D power spectrum. I saw that there's a poster about it, but I'm just wondering if that's something that you're trying to do so that you can at least see whether you are tracing the same populations. Because if you're using the Delft catalog galaxies for finding positions of your binary black holes, your binary black holes actually have the same kind of population dynamics and power spectra as those Delft galaxies.
Yes.
Does that make sense?
Yes, yes, it does make sense. And what we do is we made, for incompleteness issues, we made absolute magnitude cuts. So we see until which, in the redshift of interest, what is the brightest absolute magnitude we could see, and we volume limit our sample considering that. So we can avoid this kind of bias of having incomplete galaxies. I don't know if it was clear, but I can give you details later on.
Okay, so let's thank the speaker again.